Hello there, and welcome to Beyond the Cosmos, where the biggest questions in science are explored at the pace of a slow breath, where curiosity is never rushed, and where the universe unfolds one careful thought at a time. Tonight, we are going to sit with a strange and quietly unsettling fact, one that most people, even people who think of themselves as reasonably familiar with astronomy, have never fully absorbed. The universe, when you actually count up everything we can see, everything that shines or glows or reflects or absorbs light in any way, comes up dramatically short. Something enormous is missing. Not a small discrepancy, not a rounding error, not the kind of minor gap that careful measurement usually closes with time. A genuinely vast, genuinely confounding absence amounting to the overwhelming majority of everything that exists. We are going to spend tonight exploring exactly what is missing, how astronomers first noticed the gap, what they have proposed to fill it, and why. After nearly a century of careful searching, the most important parts of this puzzle remain stubbornly, fascinatingly unsolved. This is a story about galaxies that spin in ways they shouldn't be able to spin, about clusters of galaxies that hold together with a grip far stronger than their visible matter could possibly provide, about a universe that, by every careful accounting we have managed to perform, is composed mostly of something we cannot directly see, cannot directly touch, and cannot, even now, fully explain. Before we set off, I want to ask where you are tonight. Perhaps you are settled into bed, the blankets gathered close, the room dim and quiet around you. Perhaps you are in a favorite chair, the day finally loosening its grip on your shoulders. Wherever you are, the matter making up your body, your bed, your walls, your entire visible world, all of it belongs to a surprisingly small minority of what the universe actually contains. Tonight, we will explore the much larger majority, the part of the cosmos that remains, even after a century of patient investigation, fundamentally mysterious. If this kind of careful, unhurried exploration helps your mind settle into rest, it would mean a great deal if you tapped the like button or subscribed to Beyond the Cosmos. It helps more people who are looking for a calm voice to think alongside find their way here too. Now, let your shoulders drop a little further. Take one slow breath in and let it go without hurry, and let's begin. Let's start with the simplest possible version of the puzzle, stripped of all its later complications, because the original discovery, when you walk through it slowly, is almost shockingly direct in its implications. If you want to know how massive an object is, one of the most reliable methods available to a physicist is to study how things move around it. The Earth orbits the Sun at a particular speed, determined precisely by the Sun's mass and the distance between the two bodies. Measure that orbital speed and that distance carefully enough, and you can calculate the Sun's mass without ever needing to touch it, weigh it, or see inside it. This is one of the oldest and most powerful tricks in all of astronomy. Motion reveals mass, even when the object producing that mass cannot be directly observed in any other way. In the 1930s, an astronomer named Fritz Zwicky applied exactly this logic to a cluster of galaxies known as the Coma Cluster, a rich, densely packed grouping of galaxies bound together by their mutual gravity. Zwicky measured the velocities of individual galaxies as they moved within the cluster, and then used those velocities, combined with the basic physics of gravitational orbits, to calculate how much total mass the cluster needed to contain in order to hold those rapidly moving galaxies together. Without enough mass, the cluster's gravity would be too weak to restrain its own members, and the whole structure would simply fly apart, the individual galaxies scattering off into the surrounding darkness like marbles flung from a spinning plate. What Zwicky found was startling. The galaxies in the Coma Cluster were moving so quickly that the visible matter, the combined light of every star in every galaxy he could observe, accounted for only a small fraction of the mass needed to gravitationally hold the cluster together. By his estimate, the cluster needed to contain hundreds of times more mass than what could be accounted for by its visible stars and gas. Zwicky, writing in German in a relatively obscure astronomical journal, called this missing material Dunkelmaterie, dark matter, a name that has stuck for nearly a century since. At the time, Zwicky's finding was met with considerable skepticism, and reasonably so. It is an extraordinary claim, and extraordinary claims require extraordinary evidence. Perhaps his velocity measurements were flawed. Perhaps the cluster wasn't gravitationally bound at all, but was instead a temporary, transient grouping of galaxies that simply happened to be passing through the same region of space without truly being held together by mutual gravity. Perhaps some unaccounted source of light, faint stars too dim to detect with the instruments of the 1930s, could close the gap. For decades, Zwicky's discovery remained an intriguing but largely unresolved anomaly, sitting at the margins of mainstream astrophysics, waiting for better instruments and more careful follow-up observations to determine whether this missing mass was a genuine cosmic mystery or simply a measurement error waiting to be corrected. The next major piece of this puzzle arrived several decades later in the 1970s through the careful work of astronomer Vera Rubin, working alongside her colleague Kent Ford, studying not entire clusters of galaxies, but the internal motion of individual spiral galaxies, including our nearest large neighbor, the Andromeda Galaxy. Rubin and Ford set out to measure what astronomers call a galaxy's rotation curve, essentially a graph showing how fast stars and gas orbit the galaxy's center as a function of their distance from that center. Based on the distribution of visible matter within a typical spiral galaxy, most of it concentrated toward the bright, dense central bulge, with progressively less material out toward the fainter, more sparsely populated edges of the disk, astronomers expected rotation curves to behave in a predictable way. Stars closer to the crowded center should orbit relatively quickly, in keeping with the strong gravitational pull from all the densely packed mass nearby. Stars farther out, in the sparser outer regions where visible matter becomes increasingly scarce, should orbit progressively more slowly, since there is less visible mass interior to their orbits to provide the necessary gravitational pull. This is exactly the pattern observed in our own solar system, where Mercury, closest to the Sun's concentrated mass, whips around in just 88 days, while distant Neptune, far from that same concentrated source of gravity, takes 165 years to complete a single orbit. What Rubin and Ford actually found, when they carefully measured the rotation curves of Andromeda and dozens of other spiral galaxies, defied this expectation entirely. Rather than slowing down at greater distances from the galactic center, as the distribution of visible matter would predict, the stars and gas in the outer regions of these galaxies continued orbiting at roughly the same speed as material much closer to the center, producing what astronomers call a flat rotation curve. This flatness, persisting out to the very edges of the visible disk and, in many cases, continuing flat even beyond where visible matter could be detected at all, implied the presence of a vast amount of additional, unseen mass, distributed not in the concentrated central pattern of the visible stars, but spread out in a much larger, much more extended halo surrounding and enveloping the entire visible galaxy. This was, in a sense, Zwicky's missing mass problem reappearing in a completely different context, at a completely different scale, decades after his original, largely overlooked discovery. Rubin and Ford were not studying the motion of entire galaxies within a cluster, but the motion of individual stars within a single galaxy, and yet they were running into precisely the same fundamental issue. The visible matter, accounted for as carefully and as completely as contemporary instruments allowed, simply could not explain the observed gravitational behavior. Something else, something unseen, something far more massive than the visible stars and gas combined, had to be present, exerting its gravitational influence on the motion of everything within and around these galaxies. Rubin's findings, unlike Zwicky's decades earlier, landed in a scientific community considerably more prepared to take the implications seriously. and her careful, methodical, repeatedly confirmed measurements across dozens of different galaxies helped transform dark matter from a largely overlooked anomaly into one of the central defining puzzles of modern astrophysics. It is worth pausing here to appreciate just how much careful, patient observational work underlies this transformation. Rubin did not simply measure one galaxy and declare a universal phenomenon. She and her collaborators measured rotation curve after rotation curve, galaxy after galaxy, spiral after spiral, finding the same basic flat pattern again and again across a wide range of galaxy sizes, masses, and morphologies. This kind of repeated, consistent confirmation across many independent examples is exactly what gives a scientific finding its real weight, transforming what might otherwise be dismissed as a single anomalous measurement into a robust, well-established pattern demanding a genuine physical explanation. The explanation that gradually gained acceptance throughout the late 20th century, and that remains the dominant framework in astrophysics today, holds that galaxies are embedded within vast, roughly spherical halos of dark matter, extending well beyond the visible disk of stars and gas, providing exactly the kind of extended, distributed gravitational influence needed to explain the flat rotation curves that Rubin and Ford, and subsequently many other astronomers, observed again and again. This dark matter halo, invisible to every form of direct observation available to astronomers, nonetheless dominates the total mass of a typical galaxy, with the visible stars, gas, and dust that we can actually see and study directly representing only a relatively small fraction, often estimated at somewhere between 10 and 20% of the galaxy's true total mass. This picture, a galaxy as a small, bright, visible core embedded within a much larger, much more massive, entirely invisible halo, represents a fairly dramatic revision of how astronomers had previously thought about the basic structure of galaxies. For most of the history of astronomy, a galaxy was understood, quite reasonably, as essentially coextensive with its visible light, a disk or a sphere of stars whose boundary could be traced by simply noting where the starlight faded into the surrounding darkness. The dark matter halo concept suggests something considerably stranger, that the true extent and the true mass of a galaxy reaches dramatically beyond anything visible at all, that what we see, however beautiful and however scientifically rich, represents only the comparatively small, comparatively bright tip of a much larger, much more massive, entirely hidden structure. Having established the basic shape of the problem, let's spend some time exploring exactly how confident astronomers have become that this missing mass is genuinely real, rather than some more mundane artifact of incomplete observation or flawed theoretical assumptions, because this confidence did not arrive all at once, but was built up gradually through multiple independent lines of evidence, each one converging on the same fundamental conclusion through an entirely different observational approach. One particularly powerful and particularly elegant line of evidence comes from a phenomenon called gravitational lensing, a direct consequence of Einstein's general theory of relativity, which predicts that massive objects bend the path of light passing near them, much as a lens bends light passing through glass. When light from a distant background galaxy passes near a massive foreground object, a galaxy cluster for instance, the path of that light is subtly bent and distorted, producing characteristic, often dramatically beautiful arcs and rings in the resulting images, sometimes even producing multiple distorted copies of the same distant background galaxy, smeared and stretched around the foreground cluster like reflections in a curved mirror. The precise amount and the precise pattern of this gravitational lensing distortion depends directly and sensitively on the total mass of the foreground object doing the lensing, including any mass that might be entirely invisible to direct observation. By carefully measuring and analyzing these lensing distortions, astronomers can map out the total mass distribution of a galaxy cluster with remarkable precision, entirely independent of any assumption about how that mass is distributed between visible stars and gas on one hand, and unseen, non-luminous material on the other. When astronomers perform this kind of careful lensing analysis on galaxy clusters, the results consistently and repeatedly confirm the same basic picture that emerged from Zwicky's original velocity measurements and Rubin's rotation curve studies. The total mass required to produce the observed gravitational lensing effects vastly exceeds the mass that can be accounted for by visible stars and gas alone, often by a factor of 5 or 6 to 1. This is a genuinely independent confirmation relying on an entirely different physical phenomenon, gravitational light bending rather than orbital motion, and yet arriving at essentially the same conclusion: that galaxy clusters, like individual galaxies, contain vastly more mass than what we can directly see. Perhaps the single most visually striking and most widely discussed piece of evidence in this category comes from a system known as the bullet cluster, actually a pair of galaxy clusters caught in the dramatic act of colliding with one another. In this system, careful X-ray observations reveal the location of the hot, ordinary, visible gas that makes up most of the cluster's directly observable mass. Gas that has been slowed and distorted by the collision, lagging behind the rest of each cluster's material like a swimmer pushing through water. Gravitational lensing observations of the same system, however, reveal that the bulk of the total mass, the material actually responsible for most of the gravitational lensing effect, has not been similarly slowed or distorted by the collision, but has instead passed straight through, offering some of the most direct and most visually compelling evidence available that the universe's missing mass behaves very differently from ordinary matter, passing through the dramatic, violent collision between two entire galaxy clusters with barely any interaction at all, exactly as you would expect from a form of matter that interacts gravitationally but does not interact in any significant way through the ordinary electromagnetic forces that govern collisions between ordinary gas and dust. This brings us to a particularly important and particularly clarifying distinction that is worth dwelling on carefully tonight. The difference between matter that interacts electromagnetically, the kind of matter that makes up stars, planets, gas clouds, and indeed your own body, and matter that interacts only, or almost only, through gravity, without producing or absorbing light, without colliding and heating in the dramatic way that ordinary gas does when two galaxy clusters smash together. Ordinary matter, the protons, neutrons, and electrons that make up essentially everything visible in the universe, interacts through the electromagnetic force in addition to gravity. This is precisely why ordinary matter glows, absorbs light, scatters light, and generally makes itself visible and detectable to telescopes sensitive to electromagnetic radiation across the full spectrum, from radio waves through visible light to X-rays and gamma rays. It is also why ordinary matter, when two clouds of gas collide, as happened dramatically in the bullet cluster, experiences friction, heating, and deceleration, the same basic physics that causes air resistance to slow a falling object, or that causes two cars colliding head-on to crumple and stop rather than passing straight through one another. The universe's missing mass, whatever it ultimately turns out to be, appears to behave fundamentally differently. It exerts gravity clearly and unmistakably in exactly the way that ordinary matter does, which is precisely how astronomers detect its presence in the first place, through its gravitational influence on galaxy rotation, on cluster dynamics, on the bending of light. But it does not appear to interact, or interacts only extraordinarily weakly, through the electromagnetic force, which is why it does not glow, does not absorb or scatter light in any detectable way, and passed straight through the violent collision at the heart of the bullet cluster without experiencing the kind of friction and deceleration that dramatically slowed the ordinary, electromagnetically interacting gas in that same system. This distinction between gravitationally interacting matter that also interacts electromagnetically and gravitationally interacting matter that apparently does not, or does so only very weakly, represents one of the deepest and most consequential puzzles in all of modern physics. It suggests that the vast majority of the matter in the universe belongs to some category of particle, or some category of physical phenomenon, entirely outside the well-understood, well-tested framework of particle physics that successfully describes every form of ordinary matter we have ever directly studied in any laboratory here on Earth. Whatever this missing mass actually consists of, it appears to be made of something genuinely, fundamentally different from the protons, neutrons, and electrons that make up everything we can see, touch, and directly study. Let's spend some time now putting actual numbers to this puzzle, because the scale of what is missing, once you actually walk through the relevant figures carefully, is genuinely staggering, considerably more dramatic than most casual discussions of dark matter tend to convey. Based on a wide range of independent lines of evidence, including the detailed structure of the cosmic microwave background that we explored in a previous episode, the large-scale clustering patterns of galaxies throughout the observable universe, and the careful measurement of galaxy rotation curves and cluster dynamics we have just walked through, astronomers have arrived at a remarkably consistent picture of the universe's overall composition. Ordinary matter, the protons, neutrons, and electrons that make up stars, planets, gas, dust, and every living thing, including every human being who has ever existed, accounts for only about 5% of the total energy content of the universe. Dark matter, the gravitationally interacting but otherwise largely invisible substance we have spent this evening discussing, accounts for roughly 27% of the universe's total energy content, more than 5 times the contribution from all the ordinary matter combined. And the remaining 68%, an even larger share than dark matter itself, belongs to an entirely separate and in many ways even more mysterious component called dark energy, the force responsible for the accelerating expansion of the universe that we explored in detail in our episode about the Great Attractor and the long-term fate of cosmic structure. Taken together, this means that the ordinary matter making up everything visible in the universe, every star, every galaxy, every planet, every person, accounts for only about 5% of everything that actually exists. The remaining 95% belongs to dark matter and dark energy combined, 2 entirely separate, entirely mysterious components that, despite their overwhelming dominance over the total composition of the universe, remain fundamentally unexplained by our current understanding of physics. This is the genuine scale of tonight's title. The universe is not missing some small, manageable fraction of its total mass and energy. It is missing the overwhelming majority of it, with the visible, comprehensible, scientifically familiar matter that makes up everything we have ever directly studied, representing only a small, almost incidental fraction of the universe's true total composition. We are, in the most literal and most startling sense possible, living in a universe built overwhelmingly from substances we do not yet understand, surrounded on every side, at every scale, by something vastly larger and vastly stranger than anything our instruments have so far been able to directly detect or characterize. Given the scale and the significance of this puzzle, it should come as no surprise that physicists have spent the better part of a century proposing, testing, and in most cases eventually ruling out an enormous range of candidate explanations for what dark matter might actually consist of. Let's walk through some of the most important of these candidates carefully, because the history of this search is itself a fascinating story of scientific persistence in the face of repeated, frustrating disappointment. One of the earliest and most intuitively appealing categories of candidates involved what astronomers call MACOs, an acronym for massive compact halo objects, essentially ordinary matter that happens to be dim, faint, or otherwise difficult to detect directly, rather than some exotic new form of particle entirely. This category includes objects like brown dwarfs, stars too small and too cool to sustain the nuclear fusion that powers ordinary stars, black holes of various sizes, neutron stars, and other compact dim remnants of stellar evolution that might, in principle, account for a significant fraction of a galaxy's otherwise unaccounted mass without requiring any new physics beyond the ordinary matter we already understand reasonably well. This was, for a time, a genuinely promising avenue of investigation, and astronomers developed clever techniques to search for these objects primarily through a phenomenon called microlensing, in which a macho passing in front of a more distant background star would temporarily brighten that star's apparent light through gravitational lensing, even though the macho itself remained too faint to observe directly. Several dedicated observational surveys conducted throughout the 1990s and into the early 2000s searched for exactly this kind of microlensing signature within our own galaxy's dark matter halo. The results of these surveys, while genuinely interesting and scientifically valuable in their own right, ultimately ruled out MACOs as a viable explanation for the bulk of the universe's missing mass. The observed rate of microlensing events was far too low to account for anything close to the total amount of dark matter inferred from rotation curves and other gravitational evidence. Whatever dark matter actually consists of, it does not appear to be composed primarily of dim stars, black holes, or other compact remnants of ordinary matter, ruling out what had initially seemed like one of the most straightforward, least exotic possible explanations for the missing mass puzzle. With MACOs largely ruled out, the search for dark matter's true identity shifted toward an entirely different category of candidates, generally referred to as WIMPs, an acronym for weakly interacting massive particles, representing an entirely new, hypothetical category of fundamental particle, distinct from any of the particles included in the well-established standard model of particle physics that successfully describes all known ordinary matter. WIMPs, as theorized, would interact with ordinary matter and with each other only through gravity and through the weak nuclear force, one of the four fundamental forces of nature, without interacting through the electromagnetic force at all, which would explain perfectly why dark matter does not glow, does not absorb or scatter light, and passes straight through collisions between galaxy clusters exactly as observed in systems like the Bullet Cluster. This category of candidate gained particular theoretical favor because certain extensions to the standard model of particle physics, developed independently to address entirely different theoretical puzzles, happened to naturally predict the existence of new particles with roughly the right properties to serve as WIMPs, a coincidence that struck many physicists as suggestive, perhaps even as evidence that nature had arranged things with a pleasing, elegant economy, solving two separate theoretical puzzles with a single new category of particle. This theoretical promise inspired a remarkable, decades-long and genuinely global experimental effort to directly detect WIMPs, primarily through extraordinarily sensitive detectors buried deep underground, shielded from the constant bombardment of cosmic rays and other background radiation that would otherwise overwhelm any faint signal from an actual dark matter particle interaction. These detectors, constructed in deep mines and tunnels around the world, wait patiently, sometimes for years at a stretch, for the extraordinarily rare event of a WIMP passing through and colliding ever so slightly with an atomic nucleus within the detector material, producing a tiny, carefully measured signal that could reveal the particle's presence and its properties. Despite this enormous, sustained, technologically sophisticated experimental effort spanning multiple generations of increasingly sensitive detectors and involving collaborations of hundreds of physicists across many different countries, no confirmed, unambiguous direct detection of a WIMP has yet been achieved. Each new generation of detector has pushed the sensitivity of these searches further, ruling out broader and broader ranges of the theoretically predicted WIMP properties, mass, and interaction strength, without ever producing the clear, repeatable, statistically robust signal that would confirm an actual discovery. This persistent, repeated non-detection has gradually, though not yet completely, eroded confidence in the WIMP hypothesis as the most likely explanation for dark matter, even as it has not yet definitively ruled out the possibility entirely. Alongside MACOs and WIMPs, physicists have proposed and continue to investigate a considerably broader and more diverse menagerie of additional candidates, each with its own distinct theoretical motivation, its own distinct experimental signature, and its own distinct history of partial success and partial frustration. Axions represent one particularly interesting alternative, originally proposed not to solve the dark matter puzzle at all, but to address an entirely separate theoretical issue in particle physics related to the behavior of the strong nuclear force. Axions, if they exist, would be extraordinarily light particles, far lighter than the WIMPs we just discussed, interacting even more weakly with ordinary matter, making them correspondingly more difficult to detect directly, but also, in principle, capable of existing in such enormous numbers throughout the universe that even their extraordinarily weak individual interactions could collectively account for the total observed dark matter density. Dedicated axion detection experiments, employing strong magnetic fields designed to occasionally convert a passing axion into a faint, detectable photon, have been operating for years without yet producing a confirmed detection. Though, as with WIMP searches, each successive generation of experiment continues to narrow the range of possible axion properties that remain consistent with the absence of any detected signal. Sterile neutrinos represent another intriguing possibility, essentially a hypothetical fourth type of neutrino, distinct from the three known types that have been extensively studied and confirmed through decades of careful particle physics experiments that would interact with ordinary matter even more weakly than ordinary neutrinos already do, making it an intriguingly plausible, if still entirely unconfirmed, candidate for at least a portion of the universe's missing mass. Primordial black holes, an idea that has experienced something of a theoretical revival in recent years, propose that some fraction of the universe's dark matter might consist of black holes formed not through the ordinary collapse of dying stars, but through the direct, extremely early collapse of unusually dense regions in the primordial universe, shortly after the Big Bang itself, before any stars had even begun to form. These primordial black holes, depending on their mass and their abundance, could in principle account for some or even all of the observed dark matter, though careful astronomical searches, including gravitational microlensing surveys and analyses of the gravitational wave signals detected from black hole mergers, have progressively constrained and narrowed the plausible range of masses and abundances that primordial black holes could occupy while still remaining consistent with everything else we have observed. Each of these candidates, and several others we have not had time to explore in detail tonight, represents a genuine, active area of ongoing theoretical and experimental research, with dedicated teams of physicists around the world continuing to refine their searches, design new experiments, and proposed new theoretical variations in the ongoing effort to finally identify exactly what this overwhelmingly dominant, yet stubbornly invisible component of the universe actually consists of. Given the remarkable persistence and the remarkable breadth of this nearly century-long search, it is worth pausing to ask a genuinely important question. Is it possible that dark matter, in the sense of some new undiscovered particle, does not exist at all, and that the observed gravitational anomalies we have spent this evening exploring instead point towards some necessary revision of our basic understanding of gravity itself? This is not a fringe or unserious question. It represents a genuine, actively pursued alternative research program within modern theoretical physics, generally grouped under the broad heading of modified gravity theories, with the most prominent and most extensively developed specific proposal known as modified Newtonian dynamics, or MOND, first proposed by physicist Mordechai Milgram in the early 1980s. The basic idea behind MOND is elegantly simple, at least in its original formulation. Rather than assuming that Newton's familiar law of gravity holds exactly the same way at every scale, and then concluding that vast amounts of unseen dark matter must be present to explain the anomalous galaxy rotation curves we discussed earlier, MOND proposes instead that the effective strength of gravity itself changes subtly at the extraordinarily low accelerations characteristic of the outer regions of galaxies, becoming somewhat stronger relative to the ordinary Newtonian prediction than conventional gravity alone would suggest. With this specific, carefully calibrated modification to the basic law of gravity, MOND can successfully reproduce the observed flat rotation curves of many spiral galaxies without requiring any additional, unseen dark matter at all, relying instead purely on the visible, directly observable matter combined with this modified gravitational law. MOND, in its original and most basic form, achieved genuine impressive success in explaining the rotation curves of individual spiral galaxies, in some cases providing a tighter, more precise fit to the observed data than the standard dark matter halo models achieve. A genuinely remarkable result that has kept this alternative research program alive and actively pursued by a dedicated community of physicists for more than 4 decades now, despite remaining very much a minority position relative to the mainstream dark matter framework. However, MOND and its various subsequent theoretical extensions have faced considerably greater difficulty explaining some of the other lines of evidence we discussed earlier tonight, particularly the behavior of galaxy clusters, where the required modification to gravity needed to match observed cluster dynamics does not align cleanly with the modification that successfully explains individual galaxy rotation curves, and especially the dramatic, visually compelling evidence from the bullet cluster, where the clear separation between the location of the visible, ordinary matter and the location of the dominant gravitational mass, as revealed through lensing, poses a considerably more natural and more straightforward explanation under the standard dark matter framework than under most currently developed modified gravity proposals. This tension between competing explanatory frameworks, dark matter as an undiscovered particle versus dark matter as a sign that our understanding of gravity itself needs revision, represents one of the genuinely live, unresolved debates in contemporary astrophysics. And it is worth spending a few more minutes appreciating exactly why this debate has proven so difficult to definitively settle, even after decades of careful theoretical and observational work on both sides. Part of the difficulty lies in the fact that both frameworks, despite their very different underlying assumptions about the fundamental nature of gravity and matter, have each achieved genuine substantive successes in explaining at least some significant subset of the relevant observational evidence. The standard dark matter framework, generally referred to as the lambda cold dark matter model, or lambda CDM, succeeds remarkably well at explaining the large-scale structure of the universe, the detailed pattern of fluctuations observed in the cosmic microwave background, and the behavior of galaxy clusters, while facing somewhat greater, though not necessarily fatal, difficulty explaining certain finer details of galaxy rotation curves and the detailed structure of dwarf galaxies, which we will explore further in a few moments. Modified gravity theories like MOND, conversely, succeed remarkably well at explaining individual galaxy rotation curves with notable precision and notable simplicity, while facing considerably greater difficulty extending that same success cleanly and naturally to the behavior of galaxy clusters and the detailed structure of the cosmic microwave background. This pattern, where each competing theoretical framework succeeds clearly in some specific domain while struggling in another, is exactly the kind of situation that makes for genuinely difficult, genuinely unresolved scientific debate rather than a simple, clean-cut case where one explanation obviously and decisively triumphs over its rival across every relevant test. It is worth being honest about this ongoing tension rather than presenting a falsely simplified picture in which dark matter has been definitively, completely established as the only viable explanation for the universe's missing mass, with no serious remaining alternative. That said, it is also worth being clear about where the current weight of evidence and the current consensus within the broader astrophysics community actually sits. The overwhelming majority of working astrophysicists and cosmologists, based on the cumulative weight of evidence from galaxy clusters, gravitational lensing, the cosmic microwave background, and large-scale cosmic structure, consider the standard dark matter framework to be considerably better supported overall than modified gravity alternatives, even while acknowledging that modified gravity continues to offer genuine, unresolved insights into certain specific puzzles, particularly regarding the detailed behavior of individual galaxy rotation curves, that the standard dark matter framework has not yet fully and elegantly explained on its own. Let's turn our attention now to a specific and genuinely puzzling complication within the standard dark matter framework itself, one that connects this evening's exploration back to themes we touched on in our previous episode about the universe's many cosmic dead zones, the question of dwarf galaxies, and the persistent, still not fully resolved discrepancies between what the standard dark matter model predicts about these small, faint galaxies and what astronomers actually observe when they study them in detail. If dark matter behaves exactly as the standard cold dark matter framework predicts, simulations of galaxy formation suggest that large galaxies like our own Milky Way should be surrounded by a very large number of smaller dark matter clumps, each one massive enough in principle to gravitationally attract and retain its own small population of stars, forming what astronomers call dwarf satellite galaxies, orbiting the much larger host galaxy, much as the Moon orbits the Earth, though on a considerably larger scale. When astronomers actually count the observed dwarf satellite galaxies orbiting the Milky Way, however, they consistently find significantly fewer than the standard dark matter simulations predict, a discrepancy that has become known, somewhat informally but quite memorably, as the missing satellites problem. This represents a genuinely interesting and genuinely unresolved puzzle, sitting in an odd, almost paradoxical relationship to the broader missing mass puzzle we have spent this evening exploring. Rather than finding more unaccounted mass than expected, as in the original dark matter discoveries we discussed earlier, astronomers studying dwarf satellite galaxies instead find less visible structure than the standard dark matter framework predicts, a kind of mirror image puzzle nested within the broader dark matter story. Several proposed explanations for this missing satellites problem have been developed and continue to be actively investigated. One possibility holds that the predicted population of small dark matter clumps does, in fact, exist in roughly the numbers the simulations suggest, but that many of these clumps have simply failed to attract and retain enough visible gas and stars to become detectable as actual observable dwarf galaxies, remaining instead as essentially dark, starless clumps of dark matter, present and gravitationally real, but invisible to direct astronomical observation because they never managed to form any substantial population of stars within them. Another related possibility involves the detailed physics of how relatively small dwarf galaxies form and evolve, including the disruptive effects of intense radiation from the very first generation of massive stars in the early universe, which may have heated and dispersed the gas within many small dark matter clumps before that gas had the chance to cool and condense into new stars, effectively suppressing star formation within the smallest dark matter halos and thereby reducing the observable population of dwarf satellite galaxies relative to the underlying population of dark matter clumps, which may indeed exist in something closer to the numbers the standard simulations originally predicted. There is a second, closely related puzzle within the population of dwarf galaxies that deserves its own careful exploration tonight, generally referred to as the core cusp problem, and it concerns not the overall number of dwarf galaxies observed, but the detailed internal distribution of dark matter within the dwarf galaxies that we do successfully observe and study. Standard cold dark matter simulations predict that the density of dark matter within a galaxy's halo should increase sharply and steeply toward the very center, producing what is technically called a cuspy density profile, with dark matter becoming extremely densely concentrated in a relatively small region right at the galaxy's core. When astronomers carefully measure the actual internal motion of stars and gas within the central regions of many observed dwarf galaxies, however, they frequently find evidence for a much gentler, much more gradual increase in density toward the center, producing what is called a chord density profile instead, with the dark matter spread out more evenly across the central region rather than concentrating sharply into a dense spike. This discrepancy, like the missing satellites problem we just discussed, represents a genuine, still actively debated tension between the detailed predictions of the standard cold dark matter framework and the actual, careful observations astronomers have managed to obtain of real dwarf galaxies. Proposed resolutions to this puzzle generally fall into a few broad categories, each representing a genuinely active area of ongoing research rather than a settled, fully resolved question. One category of proposed explanations suggests that the standard simulations, while broadly correct in their overall framework, have historically underestimated the complex, disruptive effects of ordinary, visible matter, stars forming, exploding as supernova, and driving powerful outward winds of gas on the detailed distribution of the surrounding dark matter. According to this explanation, these energetic processes involving ordinary matter can effectively stir up and redistribute the otherwise sharply concentrated dark matter near a galaxy's center, gradually smoothing out the originally predicted cuspy profile into something closer to the gentler chord profile that astronomers actually tend to observe, essentially through repeated, cumulative gravitational interactions between the dark matter and the more dynamically active, energetically violent, ordinary matter passing through and around it. A second category of proposed explanation suggests instead that dark matter itself might possess some additional physical property beyond simple gravitational interaction, specifically a tendency to interact weakly but non-negligibly with other dark matter particles, a property generally referred to as self-interaction. This kind of weak self-interaction among dark matter particles could, in principle, naturally smooth out the sharp central density spike predicted by the simplest standard models, producing the gentler, chord profiles observed in real dwarf galaxies without requiring any particularly dramatic or particularly disruptive influence from ordinary, visible matter at all. Both of these explanatory categories remain genuinely active areas of theoretical and observational research, and the true resolution to the core cusp problem may well involve some combination of both effects, operating together in different proportions across different specific galaxies, depending on their particular formation history and their particular detailed properties. Let's step back for a moment from these specific technical puzzles and consider the broader significance of what we have been exploring tonight. Much as we considered the broader implications of the universe's many cosmic dead zones in a previous episode, drawing together the various threads into a more complete picture of what this missing mass story actually tells us about the universe and about the process of scientific discovery itself. The story of dark matter traced from Zwicky's initial, largely overlooked observations of the Coma cluster in the 1930s, through Rubin and Ford's decisive rotation curve measurements in the 1970s, through the dramatic visual confirmation provided by systems like the Bullet cluster, and into the ongoing, still unresolved debates about the precise nature of dark matter particles and the detailed puzzles posed by dwarf galaxies, represents one of the longest-running, most carefully documented examples of scientific persistence in the face of genuine, sustained uncertainty that the history of modern physics has to offer. This is worth dwelling on because it offers a particularly clear and particularly instructive illustration of how careful science actually proceeds when confronting a genuinely difficult, genuinely unresolved puzzle. Unlike many of the cleaner, more straightforward scientific stories often told in popular accounts, where a single decisive experiment or a single brilliant insight resolves a long-standing mystery in one dramatic stroke, the dark matter story has unfolded gradually, incrementally, through the patient accumulation of multiple independent lines of evidence, each one adding additional weight and additional confidence to the overall picture, even as the most fundamental question at the heart of the entire puzzle, what dark matter actually is, made of what kind of particle or what kind of physical phenomenon, remains genuinely, stubbornly unresolved nearly a century after Zwicky's original observations. This pattern of partial, incremental progress, accumulating substantial confidence about the broad outlines of a phenomenon, while the deepest, most fundamental question at its core remains unanswered, is, in many ways, a more typical and more representative picture of how science actually advances than the cleaner, more dramatic narratives often presented in popular science communication. Real scientific progress is often messier, slower, and more genuinely uncertain than these simplified narratives suggest, involving long periods of patient, incremental advancement punctuated by occasional, genuinely significant breakthroughs, but rarely producing the kind of single, decisive, mystery-solving moment that popular accounts often favor for the sake of narrative clarity and dramatic satisfaction. Let's spend some time now exploring a particularly important and particularly clarifying piece of evidence that we have not yet discussed in detail tonight: the role that dark matter plays in the cosmic microwave background, the ancient afterglow of the Big Bang that we explored in considerable detail in our previous episode about the Boomerang Nebula and the coldest known temperature in the universe. The cosmic microwave background, as we discussed in that previous episode, carries within its subtle temperature variations a detailed record of the density fluctuations present in the universe approximately 380,000 years after the Big Bang, the same fluctuations that would eventually grow over billions of subsequent years into the galaxies, clusters, and cosmic web that we have explored across several previous episodes on this channel. The precise pattern of these fluctuations, when analyzed carefully using sophisticated statistical techniques, turns out to depend sensitively on the total amount and the total distribution of matter present in the early universe, including both ordinary matter and dark matter. When cosmologists carefully model how these early density fluctuations would have evolved under the influence of gravity, assuming a universe composed of the specific mixture of ordinary matter and dark matter, implied by the rotation curve and cluster dynamics evidence we discussed earlier, the resulting predictions for the detailed pattern of temperature variations in the cosmic microwave background match the actual observed pattern with remarkable, genuinely impressive precision. This represents yet another entirely independent line of evidence, relying on physics from a dramatically earlier epoch of cosmic history than the relatively recent galaxy rotation curves and cluster dynamics we discussed earlier, and yet converging once again on essentially the same conclusion: that the universe contains a substantial component of gravitationally interacting matter beyond what can be accounted for by ordinary, visible matter alone. Perhaps even more tellingly, the specific pattern of these cosmic microwave background fluctuations contains detailed information not just about the total amount of dark matter present, but about some of its more specific physical properties, particularly the fact that it must behave as what cosmologists call cold dark matter, meaning that the individual dark matter particles, whatever they ultimately turn out to be, must have been moving relatively slowly rather than at speeds close to the speed of light during the relevant early epochs of cosmic history, when these density fluctuations were first beginning to grow under the influence of gravity. This requirement that dark matter behave as cold rather than hot or relativistic dark matter derived independently from the detailed structure of the cosmic microwave background has played an important role in narrowing the range of viable candidate particles, generally favoring relatively heavy, relatively slow-moving particle candidates like WIMPs over lighter, faster-moving alternatives that would have produced a noticeably different and observably inconsistent pattern of early density fluctuations. There is a particularly beautiful and particularly important conceptual point embedded in this cosmic microwave background evidence that deserves careful, dedicated attention tonight: the way in which dark matter appears to have played an absolutely essential, structurally necessary role in allowing galaxies and the broader cosmic web to form at all, within the relatively limited span of cosmic time actually available since the Big Bang. Ordinary matter alone, without the additional gravitational influence of dark matter, would have struggled considerably to form the rich, complex structure of galaxies, clusters, and cosmic filaments that we observe throughout the universe today, within the roughly 13.8 billion years that have actually elapsed since the Big Bang. This is because ordinary matter, prior to the formation of the first atoms roughly 380,000 years after the Big Bang, remained tightly coupled to radiation through frequent collisions with photons, a coupling that effectively smoothed out and erased many of the small-scale density fluctuations that would otherwise have begun growing under the influence of gravity, slowing the overall process of structure formation considerably. Dark matter, crucially, does not interact with radiation in this same way, since it lacks the electromagnetic interactions that couple ordinary matter so tightly to photons during this early epoch. This meant that dark matter density fluctuations were free to begin growing under the influence of gravity considerably earlier than the corresponding fluctuations in ordinary matter, effectively giving dark matter a substantial head start in the long process of gravitational structure formation. By the time ordinary matter was finally freed from its tight coupling to radiation, dark matter had already begun forming the basic gravitational scaffolding, the early seeds of what would eventually become the filaments, walls, and voids of the cosmic web that we explored in detail in our episode about the Boötes void, providing ready-made gravitational wells into which the subsequently freed ordinary matter could rapidly fall and begin condensing into the first stars and galaxies. Without this crucial head start provided by dark matter's early, unimpeded gravitational collapse, detailed cosmological calculations suggest that ordinary matter alone would have required considerably longer than the actual age of the universe to form galaxies, and the broader cosmic web as rich and as well developed as what we actually observe today. In this sense, dark matter is not simply an interesting, curious addition to an otherwise complete cosmic story, sitting alongside the more familiar, more comprehensible ordinary matter as a kind of mysterious bonus feature. It appears to have been genuinely, structurally essential, providing the necessary gravitational scaffolding that allowed the universe's rich structure of galaxies and clusters to form within the actual finite span of cosmic time that has elapsed since the Big Bang. Without dark matter, in other words, there may well have been no galaxies, no stars, no planets, and no observers capable of investigating and wondering about any of this within anything resembling the actual timeline of cosmic history as we know it. Let's pause here and sit with the genuine strangeness and the genuine significance of that last point for a few moments, because it reframes the entire missing mass puzzle in a way that deserves careful, unhurried reflection. We began this evening's exploration with a discovery framed largely in terms of absence and mystery. Galaxies spinning faster than their visible mass should allow, clusters held together by gravitational forces exceeding what visible matter could provide, an overwhelming majority of the universe's total composition remaining stubbornly invisible to direct observation. This framing, while accurate, can make dark matter sound like a kind of cosmic inconvenience, an awkward gap in our otherwise tidy understanding of the universe, waiting to be explained away or filled in by some future discovery. But the cosmic microwave background evidence we just explored suggests something rather different and considerably more striking. That this same mysterious, largely invisible substance was not merely present alongside the formation of galaxies and the broader cosmic structure we have explored across multiple episodes on this channel, but was actually essential, structurally necessary to that formation process actually succeeding within the available span of cosmic time. The same dark matter that initially appeared through Zwicky's and Rubin's careful measurements as a kind of mysterious gravitational surplus, an unexplained excess of mass beyond what visible matter could account for, turns out, upon deeper investigation, to have been quietly doing an enormous amount of constructive essential work throughout the entire history of the universe, providing the gravitational scaffolding without which the rich, structured cosmos we inhabit, including our own galaxy, our own solar system, our own planet, and our own existence as observers capable of investigating any of this, would very plausibly never have come to exist at all. This reframing feels worth carrying forward as we continue tonight's exploration. Dark matter is not simply a gap in our knowledge, an embarrassing absence in an otherwise complete picture. It is, instead, an active, essential, constructive participant in the entire history of cosmic structure formation, quietly providing exactly the kind of gravitational foundation needed for everything else: the galaxies, the stars, the planets, and eventually the observers capable of wondering about all of it to come into being within the actual finite timescale that the universe's history has actually provided. Let's turn our attention now to the question of how astronomers and physicists are currently working to finally resolve this nearly century-long puzzle, exploring the next generation of experiments and observations that promise to either confirm a specific dark matter candidate, definitively rule out broad categories of remaining possibilities, or potentially reveal that some modification to our understanding of gravity itself is genuinely required after all. On the experimental particle physics side, Increasingly sensitive underground detectors continue to push the boundaries of WIMP detection sensitivity, probing ever smaller interaction strengths and ever broader ranges of possible particle masses, gradually narrowing the remaining parameter space where a WIMP, if it genuinely exists, could plausibly be hiding without having yet produced a detectable signal in any previous generation of experiment. Particle accelerators, including the Large Hadron Collider and its planned future upgrades, continue searching for direct evidence of new particles beyond the standard model, including potential dark matter candidates that might be produced, however briefly, in the extraordinarily high-energy particle collisions these facilities are capable of generating. On the astronomical observation side, increasingly detailed and increasingly comprehensive galaxy surveys continue refining our measurements of galaxy rotation curves, cluster dynamics, and gravitational lensing patterns across an ever broader and ever more statistically robust sample of galaxies and clusters throughout the observable universe, providing increasingly precise tests of both the standard dark matter framework and its various modified gravity alternatives. Improved measurements of the cosmic microwave background, building on the detailed work already accomplished by previous space-based missions, continue refining our understanding of dark matter's role in the earliest stages of cosmic structure formation, potentially revealing subtle details that could help distinguish between different specific dark matter candidates or different specific theoretical frameworks. There is also considerable ongoing interest in studying dwarf galaxies in even greater detail, building on the missing satellites and core cusp puzzles we discussed earlier, in the hope that a more complete and more precise understanding of these smallest, most dark matter-dominated galactic systems might provide particularly sensitive and particularly clarifying tests of the detailed properties that dark matter particles must possess, including the possibility of weak self-interactions between dark matter particles that we discussed as one potential explanation for the core cusp problem. Each of these ongoing research efforts represents a genuine active contribution to one of the longest-running and most significant open questions in all of modern physics. And there is genuine, well-founded optimism within the broader scientific community that continued patient progress along each of these multiple complementary research fronts will eventually, even if not necessarily soon, produce the kind of definitive resolution that has remained elusive for nearly a century since Zwicky's original, largely overlooked observations of the Coma cluster. Let's spend some time now considering a particularly interesting philosophical dimension of tonight's exploration, one that connects to themes we touched on in our previous episode about the universe's cosmic dead zones and the specific, fortunate circumstances that have allowed life to develop here on Earth. The question of what it means that the universe's dominant component remains, even now, fundamentally mysterious to the very observers, ourselves, who have managed to develop sophisticated enough science to detect and characterize its gravitational influence with such remarkable precision. There is something genuinely humbling embedded in this situation, a reminder that even our most sophisticated scientific achievements, the careful measurement of galaxy rotation curves, the detailed analysis of gravitational lensing patterns, the precise characterization of the cosmic microwave background, however genuinely impressive and however genuinely valuable these achievements are, have nonetheless left us in a position where we can confidently describe the overall behavior and the overall gravitational effects of the universe's dominant component, while remaining genuinely, fundamentally uncertain about what that component actually consists of at the most basic, most fundamental level. This is a different kind of scientific situation than many people might initially assume characterizes the relationship between humanity and the broader universe. We are not simply ignorant of dark matter, lacking any meaningful information or understanding about it at all. We know a great deal about how it behaves, how much of it exists, how it is distributed throughout individual galaxies and throughout the broader cosmic web, and what essential, constructive role it played in allowing the universe's rich structure to form within the available span of cosmic time. And yet, despite all of this genuine, hard-won knowledge, the single most basic question, what is dark matter actually made of, remains genuinely, stubbornly unanswered. This particular combination, extensive, detailed knowledge about behavior and effects, combined with fundamental uncertainty about underlying nature and composition, offers a genuinely interesting and genuinely instructive case study in the nature of scientific knowledge itself, illustrating that scientific understanding does not always progress as a simple, steady accumulation, moving uniformly from total ignorance toward complete understanding. Sometimes, as in the case of dark matter, science can achieve genuinely substantial, genuinely well-confirmed knowledge about the broad outlines and the overall behavior of some phenomenon, while the deepest, most fundamental question at its very core remains genuinely open, genuinely uncertain, and genuinely, fascinatingly unresolved, even after nearly a century of careful, sustained, increasingly sophisticated investigation. There is a related and equally interesting reflection worth offering here, connecting tonight's exploration to the broader theme of cosmic humility that has recurred throughout our explorations together on this channel, from the vast emptiness of the Boötes void to the gentle perpetual fall of our own galaxy toward the distant great attractor. Each of these previous explorations has, in its own particular way, revealed something about the genuine vastness and the genuine strangeness of the universe relative to the comparatively limited, comparatively familiar scale of everyday human experience. Tonight's exploration adds a particularly striking and particularly fundamental dimension to this recurring theme. Not simply that the universe is vast in its physical extent, stretching across distances and timescales that dwarf anything encountered in ordinary life, but that the universe is also, in a very real and very literal sense, composed predominantly of something we do not yet understand, something that exists all around us, exerting its gravitational influence on the very galaxy we inhabit, the very stars we observe, and yet remaining even now fundamentally outside the bounds of our current scientific understanding. This adds a particular kind of depth to the broader sense of cosmic humility that this channel regularly seeks to explore and to cultivate. It is one thing to recognize that the universe is vast, that our own planet occupies an almost vanishingly small corner of an almost incomprehensibly large cosmos. It is a somewhat different and, in its own way, even more striking thing to recognize that even the basic substance of that vast cosmos, the actual material composition of the universe we inhabit, remains substantially, fundamentally mysterious to us, even after a century of careful, increasingly sophisticated scientific investigation specifically directed at solving exactly this puzzle. And yet, much as we discussed in our exploration of the universe's many cosmic dead zones, this recognition of genuine uncertainty and genuine mystery need not translate into anxiety or discomfort. It can instead translate into a particular, genuinely valuable kind of wonder, a recognition that the universe continues to hold genuine surprises, genuine mysteries, genuine opportunities for discovery, even in a scientific era that has already achieved such remarkable, such genuinely impressive progress in understanding so many other aspects of how the cosmos actually operates. The fact that dark matter remains unexplained is not a failure of science. It is, instead, a genuine, honest acknowledgement of the current frontier of human knowledge, an invitation to continued curiosity, continued careful investigation, and continued patient, persistent effort, rather than a source of discomfort or unease about the limits of what we currently understand. Let's spend a few moments considering what dark matter's eventual discovery, whenever and however it ultimately occurs, might mean for our broader understanding of physics and of the universe more generally, much as we considered the broader implications of future great attractor research and future cosmic habitability mapping in our previous episodes. If dark matter ultimately turns out to consist of some specific category of new particle, a WIMP, an axion, a sterile neutrino, or some other candidate we have not yet even seriously considered, its eventual direct detection would represent one of the most significant discoveries in the entire history of particle physics, definitively confirming the existence of an entirely new category of fundamental particle, existing entirely outside the well-established standard model that has successfully described every previously known form of ordinary matter for the past half-century. Such a discovery would likely open up an entirely new, currently unimaginable area of physics, much as the original discovery of the electron, or the original discovery of the atomic nucleus, opened up entirely new fields of investigation that their original discoverers could scarcely have anticipated at the time. If, instead, the various modified gravity theories we discussed earlier ultimately prove correct, and the observed gravitational anomalies that originally motivated the dark matter hypothesis turn out to reflect some necessary, fundamental modification to our understanding of gravity itself, rather than the presence of any new undiscovered particle, this would represent an equally significant, equally transformative development, requiring a substantial revision to one of the most fundamental and most thoroughly tested theories in all of physics, Einstein's general theory of relativity, which has otherwise proven remarkably successful and remarkably well confirmed across an enormous range of other observational tests, from the precise orbit of Mercury to the detection of gravitational waves from merging black holes. Either outcome, the discovery of an entirely new category of fundamental particle, or the necessary revision of one of physics' most successful and most thoroughly tested theories, would represent a genuinely momentous achievement, the kind of discovery that fundamentally reshapes our basic understanding of how the universe operates at its deepest, most fundamental level. This is, in many ways, what makes the ongoing search for dark matter's true nature such a genuinely compelling and such a genuinely significant area of contemporary scientific investigation. Whatever the eventual resolution turns out to be, it promises to teach us something genuinely new and genuinely important about the fundamental structure of physical reality, something that will likely reshape entire areas of physics in ways that, much like the original discoveries of quantum mechanics or general relativity a century ago, we can perhaps only partially anticipate from our current vantage point. Let's return, for a while, to a more grounded, more immediate consideration of what all of this missing mass actually means for our own specific galaxy, the Milky Way, connecting tonight's broader exploration back to the more intimate, more personally relevant scale that closed several of our previous episodes on this channel. The Milky Way, like essentially every other galaxy that astronomers have carefully studied, is embedded within its own substantial dark matter halo, extending well beyond the visible disk of stars that we can observe directly with optical telescopes, reaching out, according to current estimates, to a distance of several 100,000 light-years from the galactic center, considerably farther than the roughly 100,000 light-year diameter of the visible, star-filled disk that we explored in detail in some of our earliest episodes on this channel. This means that our own galaxy's true extent, properly understood, reaches dramatically beyond anything visible to the naked eye or even to powerful telescopes searching for starlight, encompassing a vast, invisible halo of dark matter that outweighs the combined mass of every visible star in the Milky Way by a substantial factor, generally estimated at somewhere between 5 and 10 times the total mass of all the galaxy's visible stars and gas combined. The Milky Way we can see, in other words, The beautiful, star-filled spiral that we have explored across multiple previous episodes represents only a relatively small, relatively bright core embedded within a much larger, much more massive, entirely invisible structure that extends considerably farther into the surrounding darkness than any of the stars we can actually observe and study. This adds a particular and genuinely interesting dimension to our own cosmic address, the specific location within the universe that we explored in considerable detail during our previous episodes about the Great Attractor and the universe's many cosmic dead zones. We do not simply live within a galaxy defined by its visible stars, gas, and dust. We live within a much larger, much more massive structure, the majority of which remains entirely invisible to direct observation, surrounding and enveloping the relatively small, relatively bright visible portion that has historically defined our understanding of what a galaxy actually is. Our own solar system, our own Earth, exists not merely within the visible Milky Way, but within the much larger, much more extensive, predominantly dark structure that the visible Milky Way represents only the comparatively small, comparatively bright central portion of. There is a particularly evocative thought experiment worth walking through here. One that helps make this somewhat abstract reframing of our own galaxy's true extent feel a bit more concrete and a bit more tangible, much as similar thought experiments helped ground our understanding of the Bhuta's void's enormous scale and the Great Attractor's enormous gravitational influence in previous episodes. Imagine, for a moment, that you could somehow render the Milky Way's dark matter halo directly visible, glowing softly even though it produces no actual light of its own. If you could view our galaxy this way, from a vantage point sufficiently distant to take in its entire extent, the familiar, beautiful spiral structure of visible stars that we typically associate with the Milky Way, the structure depicted in countless illustrations and animations, would appear as a comparatively small, comparatively bright disk, embedded near the center of a vastly larger, vastly more extensive, roughly spherical halo, extending outward in every direction to distances several times greater than the diameter of the visible disk itself. From this hypothetical vantage point, the visible Milky Way that has captured human imagination and scientific attention for centuries, the spiral arms, the central bulge, the scattered globular clusters orbiting at the galaxy's outskirts, would appear almost as a kind of decorative inset, a relatively small, relatively bright detail embedded within a much larger, much more massive, fundamentally darker structure that extends considerably farther in every direction than any of the familiar visible features that we typically use to define and to picture our home galaxy. This reframing, while purely hypothetical and impossible to actually observe directly, given dark matter's fundamental invisibility, nonetheless captures something genuinely important and genuinely worth holding on to. That our intuitive, visually grounded sense of what a galaxy actually is, built up from centuries of observing visible starlight through optical telescopes, captures only a relatively small, relatively bright fraction of what a galaxy, including our own, actually consists of and actually extends across. The true Milky Way, properly understood in light of everything modern astrophysics has revealed about dark matter, is considerably larger, considerably more massive, and considerably stranger than the beautiful, familiar spiral of visible stars that has defined our understanding and our imagination of our home galaxy for as long as astronomers have been carefully studying it. As we begin moving toward the close of tonight's exploration, let's take a few moments to consider what all of this might mean for the broader, ongoing human project of understanding our place in the universe. A theme that has recurred throughout our various explorations together on this channel. From the vastness of cosmic voids to the gentle perpetual fall of our galaxy, toward distant concentrations of mass to the specific, fortunate circumstances that have allowed life to flourish here on Earth. The story of dark matter adds a particular and genuinely distinctive chapter to this broader, ongoing project. Where our previous explorations have generally revealed the universe to be vast, structured, and governed by physical laws that, however extreme their consequences when applied at sufficiently large scales, remain fundamentally comprehensible and fundamentally familiar in their underlying principles. Gravity, thermodynamics, the basic physics of expanding gas and orbiting bodies. Tonight's exploration reveals something genuinely different, that the universe's dominant material component appears to operate according to physical principles that remain, even now, fundamentally outside the bounds of what we currently understand, requiring either an entirely new category of fundamental particle, unlike anything previously discovered in over a century of careful particle physics research, or a fundamental revision to one of our most successful, most thoroughly tested physical theories. This represents a genuinely different kind of cosmic humility than the humility we have explored in previous episodes, less about confronting vast scales of space and time that dwarf human experience, and more about confronting the genuine limits of human scientific understanding itself, even after the truly remarkable progress that careful, patient scientific investigation has achieved across so many other areas of astrophysics and cosmology. We have learned to measure the size of the largest cosmic voids, to map the gravitational flows carrying our galaxy toward distant superclusters, to identify the coldest known natural temperature anywhere in the observable universe. And yet, despite all of this genuine hard-won knowledge about the universe's structure and behavior, we remain genuinely uncertain about the basic composition of the substance that makes up the overwhelming majority of everything that exists. This is, in its own way, a genuinely appropriate note to carry forward from tonight's exploration. A reminder that scientific progress, however genuinely impressive and however genuinely valuable, does not necessarily proceed towards some final, complete state of total understanding, but instead continues to reveal new layers of genuine mystery, even as it successfully resolves earlier layers of uncertainty. The universe, it seems, is patient enough and vast enough to hold genuine surprises in reserve, even for a species sophisticated enough to map its largest structures and its most extreme environments with such remarkable precision and such remarkable care. Let's hold, for these final extended moments of tonight's exploration, the full shape of everything we have discussed this evening, drawing the various threads together into something resembling a complete and satisfying understanding of the universe's missing mass and what its continued mystery actually means. We began with a startlingly direct observation, first made by Fritz Zwicky in the 1930s and dramatically confirmed by Vera Rubin and Kent Ford decades later, that the visible matter in galaxies and galaxy clusters cannot, by itself, account for the gravitational behavior actually observed, the speed at which galaxies orbit within clusters, the speed at which stars orbit within individual galaxies. We explored the subsequent, decades-long accumulation of additional, independent evidence, gravitational lensing, the dramatic visual confirmation provided by colliding clusters like the bullet cluster, the detailed structure of the cosmic microwave background, each one converging on the same fundamental conclusion: that the universe contains a vast quantity of gravitationally interacting matter that does not interact or interacts only extraordinarily weakly through the electromagnetic force that makes ordinary matter visible and detectable. We explored the remarkable scale of this missing mass, with ordinary matter accounting for only about 5% of the universe's total composition, dwarfed by dark matter's roughly 27% and dark energy's even larger 68% share. we walked through the long, persistent, often frustrating search for dark matter's true particle nature, from the largely ruled-out macho hypothesis through the extensively searched but still undetected WIMP candidates, through axions, sterile neutrinos, and primordial black holes, each representing a genuine, ongoing area of active research without yet producing the kind of definitive, confirmed detection that would finally resolve this nearly century-long puzzle. We considered the genuine ongoing tension between the standard dark matter framework and modified gravity alternatives like MOND, recognizing that both approaches have achieved genuine successes and genuine limitations, even while the broader weight of evidence currently favors the standard dark matter picture. We explored the specific, still unresolved puzzles posed by dwarf galaxies, the missing satellites problem, and the core cusp problem, each revealing genuine ongoing tension between theoretical prediction and careful observation that continues to motivate active research. And we considered the genuinely essential, genuinely constructive role that dark matter appears to have played throughout the entire history of cosmic structure formation, providing the necessary gravitational scaffolding that allowed galaxies, stars, and eventually observers capable of investigating any of this to come into existence within the actual finite span of cosmic history. There is one final reflection worth offering before we let tonight's exploration settle fully into rest. One that returns us to the immediate intimate scale of your own present moment, much as our previous episodes have each returned, in their closing moments, to the specific grounded reality of wherever you happen to be resting as you listen. You exist at this moment as a small, intricate arrangement of ordinary matter, the same kind of matter that makes up stars, planets, and every visible structure throughout the observable universe, representing in its totality only about 5% of everything that actually exists. And yet, surrounding you, permeating the very galaxy you call home, extending throughout the vast, largely invisible halo that envelops the visible Milky Way and provided the essential gravitational scaffolding that allowed our galaxy to form in the first place, lies the much larger, much more massive, entirely mysterious substance that this entire evening's exploration has been devoted to understanding. You are, in this sense, a product of both the visible and the invisible universe simultaneously, formed from ordinary matter that itself only managed to coalesce into stars, planets, and eventually living organisms because of the essential, structurally necessary gravitational influence of the dark matter that surrounds and envelops our entire galaxy. The atoms making up your body exist, quite literally, because an invisible, still fundamentally mysterious substance provided exactly the right gravitational conditions at exactly the right moment in cosmic history to allow the Milky Way and eventually our own solar system and eventually you to come into being within the available span of cosmic time. This is, perhaps, the most genuinely striking and most genuinely worth-carrying realization from tonight's long exploration, that the universe's deepest, most persistent mystery is not some distant abstract puzzle, safely confined to the realm of theoretical physics and particle accelerators, entirely disconnected from your own immediate personal existence. It is, instead, intimately, structurally connected to the very fact of your being here at all, woven into the deep history that allowed a small, ordinary planet orbiting a small, ordinary star within a small, ordinary corner of an otherwise vast and largely dark galaxy to develop the specific conditions necessary for a consciousness capable of lying here, now, in whatever quiet corner of the world you currently occupy, thinking carefully about exactly this remarkable, unresolved cosmic story. The night has grown quiet now, and the vast, largely invisible structure that surrounds and envelops our own galaxy can settle, gently, into the background of your awareness, not as a source of anxiety about the limits of human knowledge, but as a quiet, genuine source of wonder at just how much remains to be discovered, even after a century of careful, patient, increasingly sophisticated scientific investigation. Somewhere out there, extending far beyond the visible boundary of our own Milky Way, the dark matter halo that provided the essential gravitational foundation for our galaxy's entire existence continues its silent, invisible work, exerting its steady gravitational influence on every star, every planet, every observer within the galaxy's vast extent, without ever revealing, even now, exactly what fundamental substance or fundamental physical principle it actually consists of. Physicists continue their patient search in deep underground laboratories and at powerful particle accelerators for the specific signature that might finally reveal dark matter's true nature, while astronomers continue refining their careful measurements of galaxy rotation curves, gravitational lensing, and the cosmic microwave background, gradually narrowing the range of remaining possibilities even without yet arriving at a final, definitive answer. And here, in this specific, quiet, comfortable moment, none of that ongoing uncertainty needs to feel unsettling. It can instead feel like an invitation, a reminder that the universe continues to hold genuine mysteries, genuine opportunities for discovery, even within a scientific era that has already achieved such remarkable, such genuinely impressive progress in understanding so many other aspects of how the cosmos actually operates. The universe is missing something huge, genuinely, substantially, by every careful measurement astronomers have managed to obtain. And in that genuine, persistent absence lies not a source of unease, but a quiet, ongoing invitation toward continued curiosity, continued wonder, and continued patient, careful investigation. If tonight's exploration of the universe's missing mass has given you something worth carrying gently into rest, you are always welcome back at Beyond the Cosmos, whenever curiosity calls you toward another of the universe's genuine, unresolved mysteries. There is always more to discover, always another careful measurement waiting to reveal some new facet of how the cosmos actually operates, and always, here, a calm and curious space to explore those discoveries together. For now, let the vast, invisible structure surrounding our galaxy settle quietly into the background where it belongs, and let your own small, intricate, ordinary matter rest peacefully, here, now, within the much larger, much stranger universe that made your existence possible in the first place. Let's go back, for a while, and spend some additional time with a question we touched on only briefly earlier. Exactly how astronomers go about measuring something as seemingly intangible as the mass of an entire galaxy cluster, because the specific techniques involved, much like the careful, patient methods we explored when discussing the Great Attractor in a previous episode, are themselves a genuinely fascinating part of this story. Beyond the velocity measurements that Zwicky originally employed, and the gravitational lensing techniques we discussed in some detail, astronomers have developed a third major independent method for measuring cluster mass, relying on the hot, diffuse gas that fills the space between individual galaxies within a cluster, generally referred to as the intracluster medium. This gas, heated to temperatures of tens of millions of degrees by the gravitational energy released as it falls into the cluster's deep gravitational well, glows brightly in X-rays, providing astronomers with a third, entirely independent way of probing a cluster's total mass. The basic logic behind this X-ray method works as follows. In order for the hot intracluster gas to remain in a stable, roughly unchanging configuration, rather than either collapsing further inward under gravity or expanding outward and escaping the cluster entirely, the outward pressure produced by the gas's high temperature must be carefully balanced against the inward gravitational pull produced by the cluster's total mass. by carefully measuring the temperature and the density of this X-ray emitting gas at different distances from the cluster's center, astronomers can calculate exactly how much total gravitating mass must be present to maintain this delicate balance, entirely independent of any assumption about how that mass is distributed between ordinary, visible matter and dark matter. When astronomers apply this X-ray method to galaxy clusters, the results once again confirm the same basic picture that has now emerged from velocity measurements, gravitational lensing, and the cosmic microwave background. The total mass required to explain the observed temperature and pressure of the intracluster gas vastly exceeds what can be accounted for by the combined mass of visible stars and the X-ray emitting gas itself. This represents yet another entirely independent confirmation, relying on yet another entirely distinct physical phenomenon and yet another entirely distinct observational technique, and yet converging once again on essentially the same fundamental conclusion about the universe's missing mass. The remarkable consistency of these independent methods, velocity dispersions, gravitational lensing, X-ray gas dynamics, and the cosmic microwave background, each developed using entirely different observational techniques, each relying on entirely different underlying physical principles, and each converging on essentially the same quantitative picture of how much additional, unseen mass must be present, represents one of the most genuinely compelling aspects of the overall case for dark matter's existence. It would be one thing if a single observational technique, subject to its own particular biases or its own particular sources of systematic error, repeatedly suggested the presence of missing mass. It is considerably more compelling and considerably harder to dismiss as some kind of subtle measurement artifact when 4 or 5 entirely independent techniques, each with its own distinct potential sources of error, all converge on essentially the same conclusion. Let's also spend some time exploring a particularly interesting historical wrinkle in this story that we have not yet discussed tonight: the considerable delay, spanning several decades, between Zwicky's original 1933 observations and the broader scientific community's eventual acceptance of dark matter as a genuine, serious puzzle requiring careful investigation. Because understanding why this delay occurred offers valuable insight into how scientific communities actually evaluate and eventually accept genuinely surprising, genuinely paradigm-challenging claims. Several factors likely contributed to this lengthy delay. Zwicky himself, by most historical accounts, was a brilliant but also famously combative and famously difficult scientist, known for clashing repeatedly with colleagues and for a communication style that some contemporaries found abrasive. Factors that may have contributed to his specific dark matter claims receiving somewhat less careful, somewhat less charitable attention from the broader astronomical community than they might otherwise have received from a different, more diplomatically inclined messenger. Additionally, the observational techniques and the underlying theoretical framework available in the 1930s remained considerably less developed than what would become available by the 1970s when Rubin and Ford conducted their decisive rotation curve measurements. The instruments available to Zwicky, while impressive for their era, simply could not provide the kind of precise, statistically robust, repeatedly confirmed measurements across many independent galaxies that would eventually prove so persuasive when Rubin and Ford's considerably more refined observations became available decades later. There is also a more general and more broadly applicable lesson embedded in this historical delay, one relevant well beyond the specific case of dark matter. Scientific communities, quite reasonably, tend to require a substantial accumulation of careful, repeated, independently verified evidence before fully accepting a genuinely surprising claim that challenges existing assumptions, particularly when that claim implies the existence of some entirely new, previously unanticipated component of physical reality. This kind of careful, somewhat conservative skepticism, while it can occasionally delay the acceptance of claims that later prove entirely correct, as happened with Zwicky's original dark matter observations, also serves an important and genuinely valuable function, helping to filter out the inevitable false claims and measurement errors that any sufficiently large, sufficiently active scientific community will periodically generate, ensuring that genuinely transformative claims, when they are eventually and broadly accepted, rest on a sufficiently solid, sufficiently well-verified evidential foundation to support the substantial theoretical weight that acceptance of such a claim ultimately requires. This pattern of an initially overlooked or underappreciated discovery eventually achieving broad scientific acceptance only after decades of subsequent independent confirmation recurs throughout the history of science more broadly, and Zwicky's dark matter observations represent merely one particularly well-documented and particularly consequential example of this broader, recurring pattern. Let's turn our attention now to a topic we have not yet explored in any detail tonight, despite its considerable relevance to everything we have discussed so far. The question of how dark matter is actually distributed throughout the universe on the very largest scales, connecting tonight's exploration back to the cosmic web concept that we explored in considerable detail during our episode about the Butter's void. Just as ordinary, visible matter throughout the universe is not distributed uniformly, but instead clusters into the rich, web-like pattern of filaments, walls, clusters, and voids that we explored in that previous episode. Dark matter throughout the universe follows an essentially identical large-scale pattern, clustering into precisely the same filaments, walls, and voids that define the visible cosmic web, simply existing in vastly greater total quantity than the ordinary, visible matter that traces out and reveals this same underlying structure to our telescopes. In fact, according to the standard cosmological framework, the basic process of cosmic structure formation that produced the cosmic web in the first place was driven predominantly by dark matter, with ordinary, visible matter essentially following along, falling into the gravitational wells that dark matter had already begun carving out through its own earlier, unimpeded gravitational collapse, a point we touched on earlier when discussing dark matter's essential, structurally necessary role in cosmic structure formation. The beautiful, intricate pattern of filaments and voids that astronomers map using galaxy surveys, tracing the positions of visible galaxies throughout the observable universe, is, in this sense, something like a visible tracer, a kind of cosmic paint revealing the much larger, much more fundamental underlying skeleton of dark matter that actually does most of the gravitational work in shaping the universe's overall large-scale structure. This means that the Butter's void, which we explored in considerable detail in an earlier episode, the largest known void in the observable universe, represents not merely an absence of visible galaxies, but a correspondingly enormous absence of dark matter as well. An underdense region extending across the same vast volume in both its visible and its invisible matter content simultaneously. Similarly, the great attractor, the massive concentration of gravitating matter that we explored in detail in another previous episode, derives the overwhelming majority of its enormous gravitational pull not from the visible galaxies clustered within and around it, but from the correspondingly enormous concentration of dark matter that accompanies and indeed substantially exceeds that visible galaxy population in total mass. This reframing adds a particularly satisfying layer of connection between several of our previous explorations on this channel, revealing that the vast cosmic structures we have spent considerable time exploring, the great voids, the massive attractors, the filaments and walls of the cosmic web, are, at their most fundamental level, primarily structures defined by dark matter's distribution throughout the universe, with the visible galaxies that we can actually observe and study directly representing merely the comparatively faint, comparatively sparse, but scientifically invaluable visible tracer that allows us to map and to study this much larger, much more fundamental and largely invisible cosmic architecture. There is a particularly interesting and particularly important technical point worth exploring here in some additional depth. The specific computational techniques that cosmologists use to simulate how dark matter and ordinary matter together produce the observed large-scale structure of the universe, because these simulations have become an absolutely indispensable tool for testing and refining our understanding of dark matter's properties and behavior. Modern cosmological simulations run on some of the world's most powerful supercomputers model the gravitational evolution of enormous numbers of individual dark matter particles, sometimes numbering in the trillions, representing the dark matter content of a simulated volume of the universe potentially spanning hundreds of millions or even billions of light-years across. These simulations begin with initial conditions carefully calibrated to match the detailed pattern of density fluctuations observed in the cosmic microwave background, and then track how gravity, acting according to the well-established and thoroughly tested laws of general relativity, causes these initial fluctuations to grow and evolve over the simulated equivalent of billions of years of cosmic history. The results of these simulations, when compared against the actual observed large-scale structure of the universe, mapped through extensive galaxy surveys, have proven remarkably successful at reproducing the overall pattern of filaments, walls, clusters, and voids that astronomers actually observe, providing yet another important independent line of supporting evidence for the standard cold dark matter framework. The basic statistical properties of the cosmic web, including the characteristic sizes of voids, like the Booter's void, and the characteristic masses of superclusters, like the one anchored by the Great Attractor, emerge naturally from these simulations, without requiring any special, fine-tuned adjustments, simply as the natural, predictable consequence of dark matter's gravitational evolution starting from initial conditions calibrated against the cosmic microwave background. It is precisely these same large-scale cosmological simulations, however, that originally predicted the substantially larger population of small, dark matter clumps and corresponding dwarf satellite galaxies that we discussed earlier in connection with the missing satellites problem, illustrating an important and genuinely instructive point about how this kind of large-scale computational modeling actually functions within the broader scientific process. These simulations succeed remarkably well at reproducing the largest, most prominent features of cosmic structure, the great voids, the massive superclusters, the overall statistical pattern of the cosmic web, while facing somewhat greater, though not necessarily fatal, difficulty matching some of the finer, smaller scale details, particularly regarding the population and the internal structure of the smallest dwarf galaxies. Exactly the kind of nuanced, partial success and partial difficulty that we discussed earlier as being genuinely characteristic of how real scientific theories actually perform when tested carefully against the full range of available observational evidence. Let's spend some time now considering a particularly compelling piece of evidence for dark matter that emerged relatively recently in the broader history of this puzzle. One that connects this evening's exploration to the gravitational wave astronomy that has opened up an entirely new observational window onto the universe over the past decade. The search for primordial black holes through their gravitational wave signatures. When the Laser Interferometer Gravitational Wave Observatory, commonly known as LIGO, first detected gravitational waves from a merging pair of black holes in 2015, an achievement representing one of the most significant astronomical discoveries of the 21st century so far. The masses of the colliding black holes involved in that first detection and in several subsequent detections turned out to be somewhat larger on average than astronomers had generally expected based on existing theoretical models of how black holes typically form through the collapse of massive dying stars. This unexpected pattern in the observed black hole masses led some researchers to propose that at least some fraction of these detected black hole mergers might involve primordial black holes. The hypothetical category of dark matter candidate we briefly discussed earlier formed not through the ordinary collapse of dying stars billions of years after the Big Bang, but through the direct collapse of unusually dense regions in the very early universe, shortly after the Big Bang itself. If even a modest fraction of the universe's total dark matter consists of these primordial black holes, gravitational wave observatories like LIGO and its international counterparts might, in principle, be able to detect the distinctive gravitational wave signatures produced when two such primordial black holes merge, offering an entirely new, entirely independent observational channel for investigating one of the remaining viable dark matter candidates. This remains, it should be said clearly, a genuinely active and genuinely unresolved area of ongoing research, with the broader astrophysics community still actively debating exactly how much, if any, of the observed population of merging black holes detected by gravitational wave observatories can plausibly be attributed to primordial black holes, as opposed to the more conventional, better understood population of black holes formed through ordinary stellar collapse. But the very fact that an entirely new observational technique, gravitational wave astronomy, completely unavailable to astronomers prior to 2015, has already begun contributing meaningfully to the decades-long search for dark matter's true nature illustrates something genuinely important about how this particular scientific puzzle continues to benefit from entirely new technological and observational capabilities as they become available, opening up promising new avenues of investigation that simply did not exist for previous generations of researchers working on this same fundamental question. Let's turn our attention to a slightly different but closely related question. What, if anything, can the detailed study of our own solar system tell us about dark matter, and why, despite being surrounded by the same galactic dark matter halo that envelops the entire Milky Way, have astronomers been unable to detect any direct, local evidence of dark matter's presence within our own immediate solar neighborhood? This is a genuinely interesting question, because if dark matter is indeed distributed throughout the galaxy's halo in the manner that rotation curve measurements suggest, our own solar system, located within the disk of the Milky Way at a considerable distance from the galactic center, should itself be passing continuously through a steady, ambient flow of dark matter particles, even as the Sun and its planets continue their roughly 230 km/s orbital journey around the galactic center. Estimates of the local dark matter density in our immediate solar neighborhood, derived from the same broader rotation curve measurements and galactic modeling techniques that originally revealed the dark matter puzzle in the first place, suggest that a relatively modest but non-negligible quantity of dark matter should be present throughout the volume of space occupied by our solar system, distributed diffusely rather than concentrated into any particular object or region, given dark matter's general tendency, observed consistently across many other galaxies, to form smooth, extended halos rather than dense, compact clumps. This local dark matter density, while genuinely present according to the broader theoretical framework, turns out to be far too low and far too weakly interacting with ordinary matter to have produced any detectable effect on the orbits of planets within our solar system or any other directly observable local phenomenon that astronomers have so far been able to identify and measure with sufficient precision to distinguish from the ordinary, well-understood gravitational effects of the Sun, the planets, and other ordinary matter within the solar system. This is precisely why the various underground particle detectors we discussed earlier in tonight's exploration require such extraordinary sensitivity and such painstaking, patient experimental technique. They are attempting to detect the extraordinarily rare, extraordinarily weak interactions between this very low-density, very weakly interacting local dark matter population and the ordinary atomic nuclei contained within their carefully designed detector materials, a genuinely difficult experimental challenge precisely because the dark matter actually present within our own solar system, while real and theoretically well-motivated, exists in such low density and interacts so weakly that detecting its presence directly requires pushing experimental sensitivity to truly extraordinary, almost unimaginable levels of precision. Let's consider, for a few extended moments, the broader question of how confident we can actually be, given everything we have discussed tonight, that dark matter genuinely exists as some real, physical substance, as opposed to representing some more fundamental gap or error in our broader understanding of physics that future theoretical developments might eventually resolve in some entirely unanticipated way. This question deserves a careful, honest, and appropriately nuanced answer, rather than either an overly confident dismissal of any remaining uncertainty or an overly skeptical dismissal of the substantial evidence we have spent this evening exploring. The cumulative weight of evidence we have discussed tonight, galaxy rotation curves, cluster velocity dispersions, gravitational lensing, X-ray observations of intracluster gas, the detailed structure of the cosmic microwave background, and the broader pattern of large-scale cosmic structure formation represents an extraordinarily strong, extraordinarily well-corroborated case that something beyond ordinary, visible matter is exerting substantial gravitational influence throughout the universe, at every scale from individual dwarf galaxies to the largest galaxy clusters and the broadest patterns of cosmic structure. What remains genuinely uncertain, and what we have been careful to emphasize throughout tonight's exploration, is not whether some additional gravitational influence beyond ordinary matter actually exists, a question that the cumulative weight of evidence has rendered about as certain as anything in observational astrophysics can reasonably be considered, but rather what this additional influence actually consists of at the most fundamental level, whether it represents some new, currently undiscovered category of particle, or whether it instead reflects some necessary modification to our current understanding of how gravity itself behaves under certain specific physical conditions. This distinction between strong confidence in the overall phenomenon and genuine uncertainty about its ultimate underlying explanation mirrors a pattern we have encountered repeatedly throughout the various topics explored on this channel, and it represents an entirely normal, entirely expected feature of how careful science actually operates when investigating genuinely difficult, genuinely unresolved questions. We can be extraordinarily confident that something is happening while remaining genuinely uncertain about precisely why it is happening or what fundamental mechanism ultimately explains it. A combination of confidence and uncertainty that, far from representing some kind of scientific failure or embarrassment, actually represents an honest, intellectually rigorous acknowledgement of exactly how much we currently know, and exactly how much remains to be discovered about one of the most significant and most consequential puzzles in all of modern physics. Let's turn our attention now to a particularly interesting historical parallel that is worth exploring carefully tonight, one that offers a genuinely useful perspective on how the dark matter puzzle might eventually be resolved. Drawing on a previous episode in the history of astronomy, where astronomers encountered a remarkably similar pattern of unexplained gravitational anomalies. In the 19th century, astronomers studying the orbit of the planet Uranus noticed subtle, persistent irregularities that could not be fully explained by the gravitational influence of the known planets at the time. Rather than abandoning Newton's well-established laws of gravity, astronomers Urbain Le Verrier and John Couch Adams independently proposed that an additional, as yet undiscovered planet must be exerting its own gravitational influence on Uranus's orbit, and they used the detailed mathematics of orbital mechanics to predict, with remarkable precision, exactly where in the sky this hypothetical new planet should be located. In 1846, astronomers pointed their telescopes toward the predicted location and discovered Neptune almost exactly where the mathematics had indicated it should be found, representing one of the most celebrated and most dramatic triumphs of predictive theoretical physics in the entire history of astronomy. This historical episode offers a genuinely instructive parallel to the dark matter puzzle we have spent this evening exploring, and it represents one of the central hopes and central motivating examples that has driven much of the WIMP detection research we discussed earlier. The hope that dark matter, much like Neptune before it, represents a genuine, discoverable new component of physical reality whose properties can be inferred with reasonable precision from its observed gravitational effects, and whose direct detection, while requiring patient, sophisticated experimental effort, will eventually succeed, vindicating the broader theoretical framework, much as Neptune's discovery vindicated Newtonian gravity in the 19th century. It is worth noting, however, that this same basic historical episode, the unexplained orbital irregularities of a planet, eventually resolved through the discovery of an additional, previously unknown gravitating body, has a second, less commonly remembered chapter that offers a somewhat more cautionary lesson. Astronomers also noticed subtle, persistent irregularities in the orbit of Mercury, the innermost planet, and following the same successful logic that had led to Neptune's discovery, proposed the existence of an additional, undiscovered planet, sometimes called Vulcan, orbiting even closer to the Sun than Mercury itself, whose gravitational influence might explain Mercury's own observed orbital anomalies. Despite considerable searching, no such planet was ever found. The actual explanation for Mercury's anomalous orbit turned out to require not a new, undiscovered planet, but an entirely new theory of gravity itself, Einstein's general theory of relativity, developed decades later, which explained Mercury's orbital irregularities as a natural consequence of how mass curves spacetime in the strong gravitational field near the Sun, without requiring any additional undiscovered matter at all. This second historical episode offers a genuinely important cautionary counterpoint to the more celebrated story of Neptune's discovery, illustrating that unexplained gravitational anomalies, the basic kind of puzzle that originally motivated the dark matter hypothesis, have historically been resolved through two genuinely different kinds of explanation. Sometimes through the discovery of additional, previously unknown matter, as with Neptune, and sometimes through the discovery that our fundamental theory of gravity itself required revision, as with Mercury and general relativity. Both of these historical precedents remain genuinely relevant and genuinely instructive as physicists continue working to determine which of these two broad categories of explanation, new matter or new gravity, will ultimately prove correct for resolving the dark matter puzzle that has occupied us throughout this evening's exploration. Let's spend some additional time considering the specific, detailed predictions that distinguish the standard dark matter framework from modified gravity alternatives like MOND. Because understanding exactly where these two competing explanatory frameworks make genuinely different, genuinely testable predictions helps illuminate why this debate, despite decades of careful investigation, has proven so difficult to definitively resolve through observation alone. One particularly important and particularly well-studied test involves what astronomers call the Tully-Fisher relation, a remarkably tight, remarkably precise empirical relationship between a spiral galaxy's total luminosity, essentially how bright it appears, and its rotational velocity, how fast its outer regions are observed to rotate. This relationship holds with remarkable precision across an enormous range of different spiral galaxies, of vastly different sizes and vastly different total masses, a level of precision and a level of universality that some researchers have argued is somewhat easier to naturally explain under modified gravity frameworks like MOND, where the relationship emerges directly and necessarily from the specific mathematical form of the proposed gravitational modification than under the standard dark matter framework, where reproducing this same precise relationship requires a more complex, more specific set of assumptions about exactly how dark matter halos relate to the visible galaxies embedded within them across many different galaxy types and many different galaxy masses. This particular piece of evidence represents one of the genuine ongoing strengths of the Modified Gravity Research Program, and it is part of why MOND and its various theoretical descendants continue to attract serious, sustained attention from a dedicated community of physicists, despite the standard dark matter framework's generally stronger overall position when the full range of available evidence is considered together. The Tully-Fisher relation's remarkable precision and remarkable universality represents exactly the kind of specific, detailed observational test where the two competing frameworks make genuinely different predictions, and where careful, ongoing observational work continues to probe and to refine our understanding of exactly how well each framework actually performs when subjected to this particular, quite stringent empirical test. Other tests, including the detailed behavior of galaxy clusters, the specific pattern of fluctuations in the cosmic microwave background, and the large-scale statistical properties of cosmic structure formation that we discussed earlier, tend to favor the standard dark matter framework considerably more strongly, illustrating once again the genuinely mixed, genuinely nuanced pattern of evidence that has made this particular scientific debate so persistently difficult to resolve through any single decisive observational test, requiring instead the kind of careful, holistic weighing of multiple different, sometimes conflicting lines of evidence that characterizes genuinely difficult, genuinely unresolved questions at the frontier of contemporary physics. There is a particularly interesting recent theoretical development worth exploring before we move toward the close of tonight's exploration, one that attempts to bridge the gap between the standard dark matter framework and the genuine successes of modified gravity theories like MOND. The proposal that dark matter itself might possess unusual exotic properties that happen to naturally reproduce the specific MOND-like behavior observed in individual galaxy rotation curves without requiring any modification to gravity itself. Several theoretical frameworks along these lines have been proposed in recent years, generally suggesting that dark matter might behave differently under different physical conditions, perhaps becoming effectively superfluid, a state of matter we briefly touched on in our previous episode about the Boomerang Nebula, under the specific low-density, low-temperature conditions found within individual galaxy halos, while behaving more like the conventional, simple cold dark matter assumed in standard models under the different physical conditions found within larger, denser galaxy clusters. If dark matter does indeed possess this kind of context-dependent behavior, transitioning between different effective physical properties depending on the specific density and temperature conditions it finds itself in, this could potentially explain why MOND-like behavior emerges so cleanly and so precisely at the scale of individual galaxies, where the relevant superfluid-like properties might naturally dominate, while standard cold dark matter behavior, without any MOND-like modification, continues to provide the better explanation at the scale of galaxy clusters, where the different physical conditions present might prevent this same superfluid-like behavior from emerging in the same way. This represents a genuinely interesting and genuinely active area of contemporary theoretical research, attempting to capture the genuine empirical successes of both the standard dark matter framework and modified gravity alternatives within a single, unified theoretical picture, rather than treating these two approaches as entirely separate, mutually exclusive possibilities. Whether this kind of unified, context-dependent dark matter framework ultimately proves correct remains, like so much else we have discussed tonight, a genuinely open and genuinely active question requiring considerably more theoretical development and considerably more careful observational testing before any confident, well-supported conclusion can be reached. But it illustrates the kind of creative, genuinely innovative theoretical thinking that continues to characterize this particular area of physics, as researchers continue searching for the specific combination of ideas that will finally, definitively resolve the nearly century-long puzzle that Zwicky's original 1933 observations first revealed. Let's take some time now to consider what tonight's exploration might mean for how we think about the broader concept of scientific uncertainty itself, particularly in contrast to how uncertainty is sometimes discussed, often somewhat carelessly, in broader public conversations about science. There is a tendency, in some popular discussions of science, to treat scientific uncertainty as though it represents a kind of weakness or failure, a gap that responsible, rigorous science should be expected to quickly close, with persistent, long-running uncertainty somehow reflecting poorly on the scientists involved or on the broader scientific enterprise itself. Tonight's exploration of the dark matter puzzle offers, I think, a genuinely useful corrective to this somewhat mistaken way of thinking about scientific uncertainty. The fact that dark matter's true nature remains genuinely unresolved, nearly a century after Zwicky's original observations and roughly half a century after Rubin and Ford's decisive rotation curve measurements, does not reflect any particular failure or inadequacy on the part of the many brilliant, dedicated physicists who have worked carefully and persistently on this problem throughout that extended period. It reflects, instead, the genuine intrinsic difficulty of the underlying scientific question itself, a question that requires detecting and characterizing a form of matter that, by its very nature, interacts only extraordinarily weakly, if at all, with the ordinary matter and the ordinary electromagnetic radiation that essentially all of our available scientific instruments are fundamentally designed to detect and to measure. Given this genuine intrinsic difficulty, the fact that physicists have nonetheless managed to establish such a detailed, such a well-corroborated understanding of dark matter's overall gravitational behavior, its overall abundance, its overall distribution throughout individual galaxies and throughout the broader cosmic web, and its essential, structurally necessary role in the history of cosmic structure formation represents a genuinely remarkable scientific achievement, even without yet having resolved the single most fundamental question of what dark matter actually consists of at the most basic level. This combination, substantial, well-established knowledge about overall behavior combined with genuine, persistent uncertainty about ultimate underlying nature, should be understood not as a scientific failure, but as an honest, accurate reflection of genuinely difficult scientific terrain, navigated about as well as careful, patient, persistent scientific investigation could reasonably be expected to navigate it, given the genuine intrinsic challenges involved. As we move toward the true close of tonight's exploration, let's take a few final moments to consider the sheer scale of intellectual effort spanning multiple generations of scientists across many different countries and many different scientific disciplines that has gone into investigating this single persistent puzzle, because the scope of this collective effort is itself worth appreciating. Since Zwicky's original observations in the 1930s, literally thousands of professional astronomers, astrophysicists, and particle physicists have devoted substantial portions of their careers to investigating various aspects of the dark matter puzzle, developing increasingly sophisticated observational techniques, building increasingly sensitive detection experiments, running increasingly detailed computational simulations, and proposing and refining an enormous range of theoretical frameworks attempting to explain the underlying phenomenon. This represents, in its own way, one of the largest and most sustained collective scientific investigations into any single open question in the entire history of physics, rivaling in scope and in duration other major, long-running scientific investigations like the search for the Higgs boson or the ongoing effort to detect gravitational waves directly. This sustained, multi-generational collective effort reflects something genuinely important about how the broader scientific community approaches genuinely significant, genuinely difficult open questions. Not through the work of any single brilliant individual working in isolation. However important specific individual contributions like Zwicky's original observations or Rubin and Ford's decisive rotation curve measurements have undoubtedly been, but through the patient, cumulative, collaborative effort of an entire international scientific community, building incrementally on each other's work across multiple decades, gradually narrowing the range of viable explanations through careful, persistent, methodical investigation, even without yet achieving the final, decisive breakthrough that would definitively resolve the underlying puzzle once and for all. This pattern of sustained, collaborative, multi-generational scientific investigation, however slow and however gradual its overall progress, might sometimes appear relative to the more dramatic, more immediately satisfying narratives often favored in popular science communication, represents, I think, one of the most genuinely admirable and genuinely impressive features of how modern science actually operates when confronting its most significant, most fundamental open questions. The dark matter puzzle, in this sense, stands as a kind of living monument to exactly this pattern of patient, collaborative, multi-generational scientific persistence, with each new generation of researchers building carefully on the foundation established by those who came before, gradually, incrementally advancing our collective understanding of one of the universe's deepest and most consequential remaining mysteries. Let's hold, for these final moments before we close, the complete shape of tonight's long exploration, recognizing both how much we have learned together and how much genuinely remains unknown, even after this extensive, careful journey through nearly a century of patient scientific investigation. We now understand, with remarkable confidence, that the universe contains vastly more gravitating matter than what we can directly see, accounting for the rotation of galaxies, the dynamics of galaxy clusters, the bending of light through gravitational lensing, and the detailed structure of the cosmic microwave background. Each independent line of evidence converging on the same fundamental conclusion through entirely different observational techniques and entirely different underlying physical principles. We understand that this missing mass played an essential, structurally necessary role throughout the entire history of cosmic structure formation, providing the gravitational scaffolding without which galaxies, stars, planets, and eventually observers capable of investigating any of this would very plausibly never have come to exist within the actual, available span of cosmic time. And yet, despite this substantial, hard-won understanding, we genuinely do not yet know what this missing mass actually consists of, whether it represents some entirely new category of fundamental particle, still eluding detection despite decades of increasingly sophisticated experimental effort, or whether it instead reflects some necessary, fundamental revision to our current understanding of how gravity itself behaves under certain specific physical conditions. This genuine, persistent uncertainty sitting at the very heart of one of the most significant and most consequential open questions in all of contemporary physics, represents exactly the kind of honest, intellectually rigorous acknowledgement of the current frontier of human knowledge that this channel has consistently sought to explore and to honor throughout our various explorations together. The universe is missing something huge, genuinely, substantially, by every careful measurement that nearly a century of dedicated scientific investigation has managed to obtain. And in that genuine, persistent, fascinating absence lies not a source of discomfort or unease, but a quiet, ongoing invitation toward continued curiosity, continued careful investigation, and continued patient, collaborative scientific effort carried forward by each new generation of researchers building on the foundation established by Zwicky, by Rubin and Ford, and by the thousands of other dedicated scientists who have contributed to this remarkable, still genuinely unfinished story. Before we let tonight's exploration finally rest, there is one more thread worth pulling gently, because it connects this evening's story back to something genuinely human, something that sits underneath all the careful measurement and all the patient theoretical work we have walked through together. Every astronomer and physicist we have mentioned tonight, Zwicky measuring velocities in the Coma cluster, Rubin and Ford patiently tracing rotation curves through Andromeda, and dozens of other spiral galaxies. The thousands of researchers since who have built detectors deep underground, or modeled colliding clusters, or searched the cosmic microwave background for subtle clues. Each of them spent years, sometimes entire careers, pursuing a substance they could never directly see, never directly hold, never directly confirm through the most basic and most satisfying tool available to a scientist: simply looking at the thing in question. They worked instead through inference, through the careful, patient interpretation of indirect evidence, trusting that the universe's gravitational behavior was telling them something true and something real, even when that something refused, year after year, decade after decade, to reveal itself any more directly. There is a particular kind of faith embedded in this kind of work, not faith in the religious sense, but faith in the deeper, more fundamental sense of trusting that the universe is, in fact, comprehensible, that careful measurement and careful reasoning will eventually yield genuine understanding, even when that understanding arrives slowly, incompletely, and only after generations of patient, often frustrating effort. This faith has been rewarded repeatedly and substantially throughout the history of the dark matter puzzle, even without yet delivering the single final answer that would close the story completely. Each new piece of independent evidence, each new line of confirmation, each new theoretical refinement has deepened rather than undermined this confidence that the universe, however strange and however reluctant to reveal its deepest secrets, ultimately operates according to comprehensible, discoverable physical principles. This is, perhaps, the quietest and most enduring lesson tonight's exploration has to offer: that genuine scientific progress does not require immediate, complete answers in order to be genuinely valuable and genuinely meaningful. It requires only the patient, sustained willingness to keep looking carefully, to keep measuring precisely, and to keep trusting that the universe's underlying coherence will eventually reward that patience, even if the final reward arrives only after a century of careful, collaborative, multi-generational effort, and even if, as remains true tonight, that final reward has not yet fully arrived at all. The night has settled fully now, and the vast, mysterious substance that surrounds and envelops our own galaxy, providing the essential gravitational foundation for everything visible within it, can rest quietly in the background of your awareness, where it belongs, not as an unsettling gap in human understanding, but as a genuine ongoing testament to just how much wonder, and just how much genuine mystery the universe still holds in reserve, even after the truly remarkable scientific progress that careful, patient, collaborative investigation has achieved across so many other areas of astrophysics and cosmology. If tonight's long, careful exploration of the universe's missing mass has given you something worth carrying gently into rest, a quiet appreciation for both how much we have learned and how much genuinely remains to be discovered, you are always welcome back at Beyond the Cosmos. Whenever curiosity calls you toward another of the universe's genuine unresolved mysteries, there is always more to discover, always another careful measurement waiting to reveal some new facet of how the cosmos actually operates, and always, here, a calm and curious space to explore those discoveries together. For now, let the vast, invisible structure surrounding our galaxy settle quietly into the background where it belongs, and let your own small, ordinary, visible self rest peacefully, here, now, within the much larger, much stranger universe that made your existence possible in the first place. Let's close with one final, simple image, returning to the same quiet, grounded place where we began this evening's long journey together. You are here, now, made of ordinary matter, the same kind of matter that makes up every star and every visible galaxy throughout the observable universe, representing only a small fraction of everything that actually exists. Surrounding your entire galaxy, extending through the vast cosmic web of filaments and voids that we have explored across several evenings together on this channel, lies the much larger, much more massive, still fundamentally mysterious substance that gave that entire structure its shape and its foundation. You exist because of it, woven into a story that began with Zwicky's overlooked observations nearly a century ago and that continues today, in underground laboratories and at powerful particle accelerators, and in the careful, patient analysis of galaxy surveys spanning the observable universe. That story is not finished. It may not be finished for many years yet, perhaps not within your lifetime, perhaps not within several lifetimes beyond your own. But the not knowing, carried gently and without anxiety, is its own particular kind of invitation, a reminder that the universe remains genuinely, wonderfully unfinished in its revelations, genuinely capable of surprising even the most careful, most sophisticated scientific investigation that an entire century of dedicated human curiosity has been able to muster. Rest now, here, in this specific, ordinary, visible corner of an overwhelmingly invisible universe. The missing mass will still be there tomorrow, patient and silent and essential, doing its quiet gravitational work exactly as it has for billions of years, waiting, perhaps, for some future generation of careful, curious observers to finally understand what it actually is. There is one more avenue of this story worth a final, careful pass before the night fully settles, because it touches on a question many curious listeners eventually arrive at, once they have sat with everything we have covered tonight. If dark matter is so abundant, so structurally essential, and so thoroughly confirmed through multiple independent lines of evidence, why does its discovery feel, even now, somehow less culturally prominent than other major findings in modern physics? The detection of gravitational waves, the discovery of the Higgs boson, the first image of a black hole's shadow? Part of the answer likely lies in the very nature of dark matter's evidence itself. The discoveries that tend to capture broad public imagination are often those with a single, dramatic, visually striking moment of confirmation. A detector lighting up with an unmistakable signal, a photograph finally capturing something previously only theorized. Dark matter, by contrast, has never offered this kind of singular, decisive moment. Its case has been built gradually, cumulatively, across decades of patient measurement, with no one experiment or observation serving as the definitive, headline-grabbing proof. This is not a weakness in the underlying science, which, as we have spent this entire evening exploring, rests on a remarkably broad and remarkably consistent body of evidence. It is simply a different kind of scientific story, one built through accumulation rather than through a single dramatic revelation. And stories built through accumulation, however scientifically robust, do not always translate as easily into the kind of singular, memorable narrative that captures broad public attention. There is also the simple matter that dark matter's central mystery, what it actually consists of, remains genuinely unresolved, which means the story has no satisfying ending to tell, no triumphant final chapter comparable to the eventual detection of the Higgs boson after decades of theoretical prediction. We are, in a sense, still in the middle of this particular story, and stories without endings, however genuinely fascinating their middle chapters might be, often receive less sustained public attention than stories that have already reached their satisfying, dramatic conclusion. This is, in its own way, exactly why an unhurried, patient exploration like the one we have undertaken together tonight feels worthwhile. The dark matter story does not need a dramatic ending to be genuinely worth understanding and genuinely worth appreciating. Its value lies precisely in what it reveals about the ongoing, unfinished nature of scientific discovery itself, in the careful, decades-long accumulation of evidence that has brought us to a place of substantial understanding without yet reaching final resolution, and in the quiet, genuine wonder of knowing that something this fundamental, this consequential, and this close to home, woven into the very structure of our own galaxy, remains an open invitation for future curiosity rather than a closed, completed chapter in the history of human knowledge. And so, as we finally allow tonight's long exploration to rest, let the image we carry forward be this: a universe built mostly from something we cannot yet name, surrounding a smaller, brighter, more familiar universe built from the ordinary matter that makes up everything we have ever directly touched, measured, or understood. Two universes, intertwined and inseparable, one illuminating the other simply by existing alongside it, each equally real, each equally part of the same vast, unfinished story that began nearly a century ago with a careful, overlooked measurement of a single distant cluster of galaxies, and that continues tonight, quietly, patiently, in your own thoughts as you drift towards sleep. Good night.